Our next chapter is color image processing. Now we are going to start with RGB images. An RGB color image is an M cross N cross 3 array of color pixels. Each color pixel is a triplet corresponding to red, green and blue components of an RGB image at a specific spatial location. An RGB image can be viewed as a stack of 3 grayscale images that produce a color image on the screen when fed into red, green and blue inputs of a color monitor. The 3 images forming an RGB color image are referred to as the red, green and blue component images. The data class of the component images determines their range of values. The number of bits used to represent the pixel values of the component images determines the bit depth of an RGB image. The number of possible colors in RGB image is 2 raised to power b whole raised to power 3. The cat operator is used to stack the 3 component images having syntax as shown here. The order in which the images are placed in the operand matters. If all component images are identical, the result is a grayscale image. Let RGB image denote a RGB image. The following commands extract the 3 component images as shown. The RGB color space usually is shown graphically as an RGB color cube as depicted in this figure. The vertices of the cube are the primary, that is red, green and blue colors, and secondary, that is cyan, magenta and yellow colors of light. To view the color cube from any perspective, you can use custom function RGB cube as shown here. So typing RGB cube and in parenthesis Vx, Vy, Vz at the prompt produces an RGB cube on the MATLAB desktop viewed from point Vx, Vy, Vz. The resulting image can be saved to the disk using function print. Next is indexed images. An indexed image has 2 components, a data matrix of integers, that is x, and a color map matrix, that is map. Matrix map is an M cross 3 array of class double containing floating point values in the range 0 to 1. The length of map is equal to the number of colors it defines. Each row of map specifies the red, green and blue components of a single color. An indexed image uses direct mapping of pixel intensity values to color map values. The color of each pixel is determined by using the corresponding value of integer matrix x as an index into map. If x is of class double, then value 1 points to the first row in a map, value 2 points to the second row and so on. If x is of class unit 8 or unit 16, then 0 points to the first row in map. To display an indexed image, you can write I am show x, map included in parenthesis or 2 statements separately as image x and then color map map. A color map is stored with an indexed image and is automatically loaded with the image when the IamRead function is used to load the image. Sometimes it is necessary to approximate an indexed image by one with fewer colors. For this, IamApprox function is used, which is having a syntax as shown below. This function returns an array y with color map new map which has at most n colors. The input array x can be of class unit 8, unit 16 or double. The output y is of class unit 8 if n is less than or equal to 256. If n is greater than 256, y is of class double. When number of rows in map is less than the number of distinct integers values of x, same color is used to display multiple values of x. Color map can be specified by using this statement map k, colon in parenthesis equals to rk space gk space beef k in square bracket. So right side of this equation are RGB values that specify one row of a column map. The map is filled out by varying the values of k. The function whiteBG is used to change the background color of the figure, having syntax whiteBG, then include color long name in the parenthesis. So long name may be black, blue, green, cyan and so on. Or another syntax for the same is whiteBG and in parenthesis include color short name. This may be K for black, B for blue, G for green, C for cyan and so on. And finally the syntax whiteBG and in parenthesis RGB values. So this may be 000 for black, 001 for blue and so on. Next is predefined color maps. So here I have included various predefined color maps in a table form. So you can pause your video here and go through all these predefined color maps by yourself. Next is, this table shows the conversion between RGB, indexed and grayscale intensity images. Here also you can pause your video and go through these conversion components by yourself. Next is NTSC color space. The NTSC color system is used in analog television. One of the main advantages of this format is that grayscale information is separate from color data, so the same signal can be used for both color and monochrome television sets. In NTSC format, image data consists of three components, that is luminance denoted by Y, hue denoted by I and saturation, that is Q. The luminance component represents grayscale information and the other two components carry the color information of a TV signal. The YIQ components are obtained from the RGB components by using function RGB2NTSC as shown below. Similarly, the function NTSC2RGB is used to transform YIQ components to RGB components whose syntax is shown here. Next is YCBCR color space. The YCBCR color space is used extensively in digital video. In this format, luminance information is represented by a single component Y and color information is stored as two color difference components CB and CR. Component CB is the difference between the blue component and a reference value, and component CR is the difference between the red component and a reference value. So the conversion from RGB to YCBCR is done by using function RGB to YCBCR. Similarly, the function YCBCR to RGB is used to transform YCBCR image to RGB. Next is HSV color space. HSV is hue saturation value that refers to tint shade and tone. It is formulated by looking at the gray axis of the RGB color cube, which results in the hexagonally spaced color palette. Along the vertical, that is gray axis, there is a change in the size of the hexagonal plane that yields the volume depicted in this figure. Function RGB to HSV is used to convert image from RGB to HSV, whose syntax is shown below. Similarly, the function HSV to RGB is used to transform HSV image back to RGB. Next is CMY and CMYK color spaces. The secondary colors of light are cyan, magenta and yellow. These colors are also considered as the primary colors of pigments. Cyan pigment can be obtained by subtracting red light from reflected white light. Similarly, pure magenta doesn't reflect green and pure yellow doesn't reflect blue. Black pigment can be obtained from the equal amounts of cyan, magenta and yellow. Fourth color, black, can be added to produce true black, giving rise to CMYK color space. To convert from RGB to CMY and vice versa, IM complement function is used, whose syntax is shown here. Next is HSI color space. HSI is hue, saturation, intensity. Color space decouples the intensity component from the color carrying information in a color image. Figure here shows the HSI model based on color triangles and circles. Next is color transformations. Linear interpolation can be implemented by using interp1q function, whose syntax is shown below. This returns a column vector containing the values of the linearly interpolated 1D function z at points xi. Column vectors x and y specify the coordinates of the underlying control points. The elements of x must increase monotonically. The length of z is equal to length of xi. In similar manner, cubic spline interpolation is implemented using the spline function, whose syntax is shown here. Here variables z, x, y and xi are same as for interp1q. However, xi must be distinct for use in function spline. Moreover, if y contains two more elements than x, its first and last entries are assumed to be the end slopes of the cubic spline. Next is color image smoothing. To smooth a monochrome image, define a filter mask of 1s, multiply all pixel values by the coefficients in the spatial mask and divide the result by the sum of the elements in the mask. RGB color image smoothing with linear spatial filtering consists of following 3 steps. That is, first is extract 3 component images as shown. After that, filter each component individually. Let us take an example. Letting W represent a smoothing filter generated using fspatial, you can smooth the red component image as shown here. Similarly, for the other 2 component images, you can filter each component image individually. Third is reconstruct the filtered RGB image as shown. However, because you can perform linear filtering of RGB images directly in MATLAB using the same syntax employed for monochrome images, the preceding 3 steps can be combined in single step, in which you can write it as fc filtered equals to im filter and in parentheses include fc w replicate. Next is color image sharpening. Sharpening an RGB color image with the linear spatial filter follows the same procedure as smoothing, but using a sharpening filters instead. So Laplacian filter mask can be used to sharpen the blurred image FB, having syntax lap mask equals to 111 semicolon 1 minus 81 semicolon 111. Enhanced image can be computed and displayed using command fen equals to imstruct and in parentheses write fb comma im filter of fb comma lap mask comma replicate, then im show fen. So this is all included in this color image processing lecture. In our next lecture, we will discuss about wavelets. So this is all. Thanks.